we go. Okay, so we've got 20 some odd minutes here. Let me remind you what we were doing last time. We were talking about symmetry. The one I think just a terribly, terribly important topic for integration techniques. A sizable fraction, back of the envelope estimate based on memory, about 20% of the integrals that I saw in my undergraduate, zero by symmetry. And I think that's a conservative estimate. So this is a really big deal. The big idea, remember, is you need your integrand to be odd, and you need your domain to be symmetric. And if so, boom, done. Integral zero. Game over, right? It's an extremely efficient, powerful way to compute integrals. Now, a couple of warnings. You do have to have both conditions. It's a very common mistake for students to make, and it's a dangerous mistake because, again, if you make a symmetry argument that doesn't actually work as an argument, there's nothing on the page that counts as progress toward a solution, right? So, dangerous, right? So do be extra careful. Make sure that you think everything through. Check both conditions and make sure you're sure about it. The other whoopsie that I see a lot is students use a different line for the odd symmetry of the integrand and a different line for the symmetry of the domain, and that does not work. There is no such theorem. That is a crash and burn situation. So again, you got nothing if that's the case. So just be very, very careful about that. We talked about why it's true. Basically, all the terms pair up and cancel, okay? Just like with the single variable equivalent theorem. And then we talked through this example. And that's a pretty typical kind of example. We won't go through all of that again. Lastly, I talked about policies, course policies. So make sure you follow these rules, right? You can't just say zero smiley face, right? It's not about the answer. It's about the reasoning. You got to give me some reasoning. The reasoning, if you're going to use symmetry, you want to see the word symmetry. If you're using symmetry, the punchline is that the integral is zero. You do have to actually say that. Right? You do have to indicate the line that you're using, that you're claiming a symmetry argument over. You don't have to give me the complete argument, but you got to tell me what the line is. This is just a way to prevent what I'm going to call the Hail Mary pass, which, by the way, I successfully scored points as an undergrad by doing the Hail Mary pass of, there's 10 seconds left. Oh my gosh, I don't know what to do with this. It equals zero by symmetry. Handed it in. Scored. Now, I did not deserve those points. But, that's past is the past. So, but anyway, I'm obviously that's not something that I should allow. Yeah.
So, like a line of symmetry, could it be like not a boundary, like an axis? Like if it's symmetric about y equals x.
Mm-hmm. Yeah. Oh, yeah. I'm going to show you an example along those lines in a minute. Yeah, axes tend to be the more convenient ones. They're the ones that maybe leap off the page most conveniently in some cases. But I got another example coming. Any line will do. Make sure to indicate what that line is. And then the other, really important point, you do have to be right. If you claim an argument that doesn't work, it's a real problem, right? I mean, that's what we're here to do, is to make valid mathematical reasoning. So do make sure that it actually works. Okay, I'm going to encourage y'all to read this little comment here. Basically, there are other symmetry theorems, but I don't really think they're quite worth the trouble. So this is the one we've got is the big one. And another reminder: be careful, right? Anyway, it's a powerful theorem, but it is a delicate theorem. Okay, new example. Domain bounded by certain curves. Pretty easy to draw that picture. Think it through. Make sure you can draw that picture, of course. I've got an integral to compute. And what's interesting about this example to me is that it's not particularly easy to check if this integrand is odd. Right, is that odd or is it not odd? I see some odd exponents. Is that what that means? Wait a second. They add up to an even number. Is that a problem? Right? We've got a very significant where it is very much not obvious. Now, it is pretty obvious that the domain is symmetric over this line. Right? And the fact that the domain is symmetric, I'm going to say, it just leaps off the page at us in the picture, so that's not the challenge. The challenge is what in the world do we do with that integrand? Sometimes it's pretty easy to just kind of plug in. This is not one of those times. So what we've got to do in order to decide if that's odd is we've got to ask ourselves, whoops, I shouldn't have erased, there we go. Got to ask ourselves, how do we reflect over this line? What is the nature of, what's the formula for that reflection? And it's not just, you put a minus sign in front of each of x and y. It just doesn't work, right? So how do we do that? So what I want to point out, and this is a cool little trick that somebody showed me when I was y'all's age, and the big idea is you can think of any point, whatever point you might be looking at, you can think of that point as having I'm going to call it a rectangular frame. There's kind of a horizontal little line segment there, if you will, and a little vertical line segment there. And when you reflect horizontal and vertical over a 45-degree line, geometric appeal, right? I'm not going to prove this. I think this is geometrically satisfying. Horizontal becomes vertical. Missed the thing. Horizontal becomes vertical, and vertical becomes horizontal. That's a purely geometric appeal, right? But so where does this point go to? How do we do that reflection? Well, you can see the picture here for what that reflection looks like, and you can just kind of read right off of the picture what the formula for the reflection is. And there it is. So this is one of my favorite tricks for how to determine the formula for a reflection. Now, this doesn't always work. This is very delicately conditioned on this being a 45-degree line, right? Otherwise, everything gets a little weird. Hey, what do you do if the line is angled at has a slope of 4.5, right? Something weird like that? Well, we can play linear algebra games, and that's a whole digression. But it is a good exercise to think in terms of if you're reflecting over the origin, that is linear transformation. And if all you've got to do is figure out the images of the standard basis vectors to find your matrix, it's kind of doable. So that's a good one to think about. Right? Okay. All right. So once we have that reflection, now all we got to do is plug in our reflection into the integrand. And now you'll notice I stopped short of going all the way up to where the integral is. I want to avoid a confusion of variables problem. Notice our reflection is in terms of x's and y's. Notice that our integrand is also in terms of x's and y's. And we're going to compose in just a second here. So how are we going to avoid accidentally creating a confusion of variables? And what I'm going to do, let's see, you know what? I'm going to try to get all of this on the screen. That'll do. What I'm going to do is rewrite our f, this thing. I'm going to write it in terms of s and t instead of x and y. Now this is just dummy variables, so who cares, right? But it's going to be s, oh gosh, it's really hard to write at this angle. S plus t to the 7th, and then s minus t to the 3rd. Okay, so that's just rewriting our integrand. Now we can compose without any confusion of variables. And in particular, if you want to plug in this reflection, you want to plug in that reflection into f. Let's see here. I'm going to plug this into f. I'm going to take minus y comma minus x, plug it into f. Notice that, the colors, so many colors. Minus y is our s. And then, I guess I'll use this color. Minus x is our t. Everybody see what I did there? That's just plugging in, but I've plugged in a way that avoids the confusion of variables. And then you do a little algebra, right? And you know, the algebra is what it is. And the nice punchline is you'll notice that this is the exact negative of what we would have gotten had we not reflected, right? It's the exact negative, and so the function is odd. Everybody happy? All right. Here's another example, another dangerous example. This is a landmine example. And I'm not doing it to be mean. I cannot emphasize that enough. I'm doing it because the world is mean, right? And I want you to see. I want you to step on the landmine in the abstract here in class, right? And not on our exam, obviously, right? But then also not on in some future circumstance, and then your bridge falls down. Right. So this is the kind of thing where it's very tempting to get a little too excited, move a little too quickly, and draw the wrong conclusion. So let's look at our triangle T here. It has corners there, there, and there. And I mean, it is tempting to say, ooh, I have an odd integrand, and this is clearly symmetric. Game over, we win integral zero by symmetry. You see the urge. You've got a symmetric domain. You've got an odd integrand. It's just over different lines. Right? It's so dangerous. Oh my gosh. Super duper dangerous. So, yeah, the domain is symmetric over the y-axis. But this integrand, right, y cubed, is only odd when you reflect in such a way as to make y the negative of what it had been, which means you're reflecting over the x-axis. And these are not the same, and there is no symmetry argument here at all. Everybody very comfortably clear with why this is this dangerous little landmine? Okay. So there's a three-dimensional version of symmetry. It's really, really similar in the same way that we talked about in 2 dimensions, you reflect over a line. Well, in 3 dimensions, we reflect through a plane. And in fact, let's just take a quick moment to think about the verbiage here, right? Why do we call it a reflection? Because we look at mirrors. Mirrors are planes. The 3-dimensional concept of reflection is where the idea of reflection comes from in math, right? So this is actually really a very, very natural extension. Same basic idea. Again, oddness means that when you reflect the input, you negate the output, just like every example we've seen before. Symmetric means, exactly what you think it means, and you can write it down in terms of, if this, then that. But it just means that it is its own reflection. And the theorem looks exactly the same if you have an odd integrand and a symmetric domain. The integral is, color change. The integral is 0, and you gotta love it. Same warnings even. Make sure that both conditions apply, otherwise catastrophe. Make sure you use the same, not line, but now plane for each condition. Again, otherwise catastrophe. Okay, so all the same stuff, pretty much. So this next example is multi-purpose. On the one hand, it is an example of a 3-dimensional symmetry argument. That's nice. but it is also an example of how to make a good choice of what line or plane you're going to reflect through. And let me acknowledge that the previous examples I've shown you, like this one, how did we decide what line to use? By looking at the domain. The domain practically screams it. There's only one line over which this is symmetric. Let's see here. What about this one? Where did we get our idea to talk about over the y-axis? From the domain. Again. Right? Very often that's the case. Very often the domain is the best way to see it. But not always, and certainly not in this example. In this example, our domain is the unit ball, which has infinitely many symmetries. Now, if you think about it, right, here's the unit ball, centered at the origin. It's symmetric through any plane whatsoever that contains the origin. Right? There's endless different ways, endless different planes that you could choose from. And that's both good and bad. The good thing is we got options. The bad news is I've got infinitely. How do I look at and consider infinitely many options? I don't have that kind of time. Right? Okay. So what we're going to do here instead is we're going to look at the integrand. Now, I just wrote down the answer here. That's kind of, let's talk about where it came from. I looked at the integrand here, and I asked myself, do I kind of vaguely see any suggestions of oddness? And yeah, I see all three. Is my only odd exponent? I know odd powers. Okay, I'm digging it. Right? This looks like it's got potential. Now wait a second, this is going to work out. I'm going to capitalize on there being an odd exponent here. Somehow, when I plug into this, I need to stick a minus sign on the z. Z needs to turn into minus z. Right? So, whatever my plane of symmetry is, I'm going to want, let's see, do it like this. Because of that 3, right, I'm going to want my reflection formula to look like that. Now, to be fair, based on my little algebraic, wishing here, I don't even know if this thing I'm wishing for is even a reflection. This is just wishful thinking. So now you got to take a pause and ask yourself, wait a minute, if I take every point in the x, y, z space, and if I return this formula, x, y minus z, is that a reflection? Thankfully it is. And furthermore, thankfully, I can pretty easily see what it's a reflection through. It's a reflection through the xy plane. So rather than looking at a picture of the domain, sometimes you can look at the integrand, play wishful thinking games, write down a hopeful reflection, and use that to motivate what you're going to use as your plane of symmetry. Everybody see the big idea there? All right. And then, of course, the rest of it works out very nicely. By the way, you do want to take a moment real quick to recognize once this has motivated your choice of plane, just give it another quick look and confirm that the domain actually is symmetric. Right? You see I wrote that down. And just that's just for you. That's for your double checking purposes to make sure you don't whoopsie. But good prudent choice. Okay, yeah.
So for the plane and line of symmetry,
Yep.
do they have to go through the origin?
Nope.
Oh.
Nope. I mean, very often they will, but they do not have to. And I think there's at least one homework exercise where I hope I did. Yes, there's at least one exercise where it doesn't. What it does have to do is the domain's got to be symmetric through it, and the integrand's got to be odd through it. So if it doesn't go through the origin, it's a little bit less convenient to write down the reflection formulas, but it's still better than the alternative of cranking it out, the old-fashioned way. Yeah. Okay, so that's 5-5. Moving on to 5-6. We're not going to finish it in the next 2 minutes, but you'd be surprised how far we can get. We're going to go pretty quickly through this. It's really just kind of one or two ideas that we kind of generalize. Now, y'all know what it means to average numbers, right? Yawn. I am just going to rewrite that. Nothing happened there particularly. But what you notice is then I can kind of pair or group kind of these parts of the expression up and rewrite it like this. And instead of claiming this now as an average of 6 numbers, now I'm going to call this a kind of an average of 3 numbers, 4, 7, and 8. Kind of honestly just 3 numbers here, 4, 7, and 8. But I just kind of want to recognize by this sort of construction that, yeah, the 4 counts twice. See, here it is, it counts twice. And the 7 counts once, and then the 8 counts 3 times. There it is. So if you want to average numbers, but if you want some to count sort of more, then this construction right here, that construction basically just says, look, whatever the numbers are that you're going to average, like the 4, the 7, and the 8, for each one there is a corresponding weight, like this, what we call the weights. And this construction I have in blue is just a generalization of this idea of an average where we, double count, triple count, whatever. We have, some are weighted, more important than others. So this is the idea of a weighted average. And y'all will recall, of course, that's how we do grades in this course. And this example here is not quite right for our class, right? Our weights are different, and it's not just a simple matter of 4 exams. I was just trying to keep the arithmetic reasonable here. But this is totally analogous, just using different weights, to how grades are going to be computed in this course, right? So, all right, well, our hypothetical student here gets, try to get this all on the page. He gets these grades. Those are the things that we're going to be taking weighted averages of, so they go like so. And then here's the weights, right? Those weights go like so. Again, those are the weights. And then arithmetic, boom. And the weighted average, the course average for this student, computing from this formula, there it is, 2.964. So Bob here, he had a rough start on the first exam, but then he, came back and did noticeably better on the second exam, got a little cocky, didn't do as well on the third exam, and then buckled down and did better on the final. And altogether, this is average. That's and now keep in mind in this class, right, we have these bins, right? It's not quite a simple matter of rounding, but it's very close to the rounding. But anyway, we use the bins, and this is in the B bin. So everybody see how that works? Last comment, we'll call it a day. If you're not thoroughly comfortable with this, if you're not entirely clear on how grades are computed in this course, just come talk to me. I'll be very happy to talk you through it. We can do some examples, answer all your questions, whatever. I do want everyone to be very comfortable with how grades are computed in this course. So again, just come talk to me. Okay, y'all have a good rest of your day. See you later. Oh, I'm sorry, last comment. I discovered a mistake in the solutions that I had written to the exam. So I'm not going to be able to get the exam solutions posted immediately. I should be able to get them posted by middle of the afternoon or so. All right, see y'all later. Have a good one. Oh, yeah, thanks for the pen. A couple other people, I forgot who. Oh, yeah. Thank you. Yeah, good. Okay.